let us start this lecture with a thought process by legendary space technocrat Vikram Ambala Sarabhai, who was instrumental in initiating the space program of India, that we could see that we are in a position to launch Chandrayaan 2 and which is about to land on moon soon. He says that he who can listen to the music in the midst of noise can achieve great things. It is really very important statement that we should keep in mind to make our mind flowery such that we can get perfection in life. Let us now recall what we learned in the last few lectures. In the last few lectures, we initiated discussion on liquid propellant rocket engines, and towards end of this series of lectures on liquid propellant rocket engine, we also discuss about the heat transfer problems related to cooling of the combustion chamber and rocket nozzles. And this knowledge of heat transfer for developing a cooling system in case of rocket engine can not only be applied for the liquid propellant rocket engine, it can be applied for solid propellant and hybrid propellant rocket engine. And today we will be discussing about hybrid propellant rocket engine. As the name indicates that it will be basically combination of the two propellants based on its physical state, like solid or liquid, or it can be solid and gaseous fuel, and also other combinations. And keep in mind that we will be only considering the solid and liquid as it is being discussed about, and a lot of work has been done to design and develop such kind of hybrid propellant rocket engine. And this rocket engine having certain advantages and disadvantages also, and that we will be discussing, but it is between the solid and liquid propellant rocket engine. Let us now look at how this hybrid propellant rocket engine evolved through the history in a very brief manner. So, in 1930s, I.G. Farben, a German scientist, was first in working on the hybrid propellant rocket engine. And later on, of course, the Bartel and Renard around 1946 had used this concept of hybrid propellant for a ramjet engines. Of course, there was a lull after that due to the Second World War, and again people took interest in this hybrid propellant rocket engine, and around 1962 when two European countries, namely France and Sweden, initiated the research work on this hybrid propellant rocket engine again, and could manage to develop hybrid propellant rocket engine which could fly in April 1964, and that could reach an altitude of 100 kilometer. And really after that lot of work has been done, and then both the developed countries like USA and Russia and other countries have started working on this hybrid propellant rocket engine. But I will just mention few of their milestones and what they achieved. The largest hybrid rocket engine was built around mid 1980s by AMROC, and which was designed for a space booster in by using H500 engine, and which could produce thrust of 312 kilonewton, and that lasted for 70 seconds, and they had used liquid oxygen and STPB propellant in that engine. There are several programs on hybrid propellant rocket engine across the globe, but unfortunately it is not really being used very much by various space agencies. And let us look at a schematic of a typical hybrid propellant rocket engine that is being shown here in this diagram. If you look at, this is your rocket hybrid propellant rocket engine system, what I have shown here, and it is having various components like a nozzle, and there is a motor grain or the rocket motors, and this is your fuel grain, and this portion is your fuel grain, and in which of course, this is your port, this portion is your port where the gases will be passing through, and this is having injectors, and this total is known as basically combustion chamber. And this combustion chamber also contains the igniters, there will be injector which is not shown here, and then this combustion chamber is connected to a feed system. We have already discussed about feed system in case of liquid propellant rocket engine. It is similar to that. Generally, very simple system is being used in this case, as only one liquid line has to be designed for this. And in this case, the liquid oxidizer is containing in a tank. This is your liquid oxidizer, which has to be pressurized by using the gas pressure feed system, and this is your gas pressurization tank. And of course, to control that, you are having pressure regulating valve which is not shown here, which will be between the gas pressurization tank and the liquid oxidizer tank. There is a diaphragm which will be separating the gas and the liquid oxidizer. Beside this, it will be having control valve. This is your control valve. So, if you compare this hybrid propellant rocket engine with the liquid propellant rocket engine, this is much simpler, and also it is easy to fabricate and design as compared to liquid propellant rocket engine. So, as I told earlier that it uses basically two kinds of propellants based on the physical state. One is solid, other is gas or the liquid, and we will be mostly discussing with the when the fuel is in solid state and oxidizer in liquid state, but it can be other way around as well, like the oxidizer will be in solid state and fuel can be in liquid state, but very rarely people have used it, and however, there is a possibility of designing that. And similarly, we can have a solid fuel and the oxidizer can be gas as well, but then it will be for a smaller engine. But if you want to have a larger powerful engine, then naturally one has to go for solid and liquid combination rather than solid and gas combination or the liquid or gas combination. So, as I told earlier that hybrid rocket engine has advantages over the liquid propellant rocket engine, especially in terms of simplicity, safety and cost, as it is having less number of components as compared to the liquid propellant rocket engine. Let us now look at characteristics feature of a hybrid propellant rocket engine. The specific impulse of the hybrid propellant rocket engine lies above the solid propellant engine. However, it will be lower than that of the maximum value of the liquid propellant rocket engine, and its specific impulse varies even during the steady state operation, because of fact that there will be variation of oxidizer and fuel mixture ratio along the length and also along the time, and that is really one of the problems one has to look at it, and it has the ability to change the thrust level smoothly over a wider range as compared to the solid propellant rocket engine. Its operation can be switched off and on easily during flight, unlike the solid propellant rocket engine. It has relatively lower system cost as compared to the liquid propellant rocket engine. It has higher safety envelope during the storage of propellant and operation of the rocket engine as compared to the solid propellant rocket engine and liquid propellant rocket engine. Its propellant utilization is much lower than that of the solid propellant rocket engine, as the certain sliver of the fuel propellant remains unutilized at the end of its operation as compared to solid propellant rocket engine. So, let us look at a schematic of a typical solid propellant rocket engines, what we had seen. I just want to discuss little bit again. Of course, it will be having a combustion chamber with a CD nozzle, and you can look at this is your solid propellants grain, and this is the port in which the oxidizer will be coming through. This is your injector plate through which the liquid fuel will be atomized, being fed by the feed system, and there is a spray. Of course, there is a igniter which will ignite the combustion in this combustion chamber. But keep in mind there is another component which is there, this is known as mixing chamber, which will not be there in case of your liquid propellant engine. And that is very important, because the fuel and oxidizer has to be mixed and burned properly before really getting expanded in the CD nozzle. Of course, it is having a controlling valve as a part of feed system, and liquid oxidizer tank is having a pressure regulating valve and the high pressure gas tank, and that will dictate how much time duration one can have this engine to be operated. And there is a diaphragm, as I told, and that will separate the liquid oxidizer tank with the high pressure gas, which happens to be inert gas. Generally, this inert gas is being used. And let us look at different kinds of propellant can be used for hybrid propellant rocket engine, and some of the fuel which are being used are polymers, polyethylene, STPB, that is hydroxyl terminate polybutadiene, CTPB, paraffins, and several others, and whichever will be can be used as a fuel in case of solid propellant, that can be. But whereas the oxidizer generally being used is liquid oxidizer, hydrogen peroxide, nitrogen tetroxide, white fuming nitric acid, red fuming nitric acid, and several others. And as I told earlier, that we need to have the grain like your solid fuel grain. This is basically solid fuel grain, and the grain configuration will be playing a major role so for the performance of the hybrid propellant rocket engine concerned, because it will be dictating the burning surface, and it hence it affects the thrust law and its level of the producing the thrust. And let us consider a cylindrical solid fuel grain, which is shown here, and in this case this is your oxidizer, and which will be there, and then as a result the propellant will be burning in these directions, and the thrust level will be limited by that, and it will be dependent not only the diameter of this solid fuel grain, but also it will be depending on the length, and this is your length. So, if you want to have a higher thrust and if diameter of the engine is limited due to some reason, then naturally one can get higher thrust by increasing the length. So, that is the limitation of cylindrical solid fuel grain. Hence, the single port grain is not preferred in case of hybrid propellant rocket engine, particularly for high thrust level engine, as its regression rate is almost 3 times less as to that of the solid propellant rocket engine. So, therefore, the multi port fuel grain is being designed and developed. So, let us look at a typical multi port fuel grain, and this is having a grain at the center, and this is the another side ports and having a basically truncated shape, or we call it as a pie shaped combustion ports. And keep in mind, this is known as wave, and if you look at, this is the thickness of the wave is double here in this case, and when it is burned, then the naturally this surface will be moving in this perpendicular to that, and there will be also a round one, and this will be way it will be moving. Now, if it is this space, the wave space here to there, that has to be properly done, and in case these are meeting, and this also if you look at, it will be also moving in the circular manner, it is goes on increasing, it is moving this way, in the opposite way in the this pie shaped combustion port. Naturally, a situation will come that it will be structurally very weak, because of the fact that it is thinning down towards end, it may lead to the some kind of falling down on the port itself. So, therefore, one has to be careful in designing these kind of multi port fuel grains. And for that, of course, one can be use a separator kind of things, and which will be having certain things, so that it will give structural rigidity, that we will be discussing little later on. Question arises, what are the challenges of designing a multi port grain? Let us take an example just to illustrate that, and let us consider that this is a circular diameter, this is your basically the fuel grain, the black one, and these are all the port. And if I start with 4 port, then naturally this is too small in that whole diameter if you look at, and if I will do that, to start with, the velocity will be very very high in this for a particular mass flux of oxidizer. Then of course, the regression rate will be also dependent on the velocity with which, as you go and see that, and then this will be moving out. There might be a situation where the regression rate will be goes on increasing. Now, the wave has to be designed properly, and then it may come over here, and similarly it may come over here, and then at the towards end this whole region will be coming into picture. So, then that will be also causing some problem, and in this case the regression rate to start with very high. Then in order to overcome that problems and of the smaller holes, then one can go for a little bigger one on a certain pitch circle, and of course, keep in mind there is no central hole here, and sometimes central hole has to be designed properly. This is your central port, and in this case of course, one can overcome the initial problems of very high velocities, but however, the volumetric efficiency of this will be little lower as compared to that, and then you may face problem at the end of it. So, similarly, I can goes on increasing this diameter to start with this multi ports, but again the volumetric efficiency will be lower as compared to the previous case. And if you look at, if it goes on increasing, as I look at here, there is this space of the propellant, when it will be increasing in size, this space of propellant will be just not having any support. So, it may fall it down, and then it may lead to the little increase in the pressure, chamber pressure of the this multi port design. So, therefore, one has to be very careful while designing this thing. So, if you want to have a higher thrust and combustion efficiency, then of course, we will have to go for multi-port grain, and also having a mixing chamber at the rear end, so that both the fuel and oxidizer will be mixed properly before it is getting expanded in the CD nozzle, so that the thrust will be higher. So, one has to be careful about that, and let us look at the processes during the combustion of hybrid propellant rocket engine, which I have shown here. And this is your fuel grain, and if I consider that it is a non-metallized fuel grain, that means it is not having metal particles. Generally metal particles are being added to increase its burn surface area, to burn rate or the regression rate. And if there is a flame or you ignite this mixture, such that flame will be formed, and generally flame is formed little away from the burning surface area, and this is your burning surface. These are the burning surface to start with, and then what will happen? This will be receding this burning surface area in this direction, right, as it is going, and of course, there is a flow which is coming. This is your oxidizer and having velocity v infinity x, and it is passing through that. It is similar to like a boundary layer, you can say. As it is regressing out, then there will be the solid will be converted into gas, and that will be moving into in this direction. And there might be some kind of a particulates which will be solid particles, it may be a metal or it may be a soot particles, and there is of course, the liquid droplets which will be there because of the liquid oxidizer is being used. And keep in mind that this will be having a flame, and generally a diffusion flame is being formed, and this is will be giving the heat over to this place on the solid surface due to the convection, and near it will be conduction, and also this there will be the solid surface also will be radiating the heat because it will be at high temperature. And beside this particulate also will be radiating the heat, but we will be not considering the radiation. And if you look at this zone is basically known as the fuel vapor zone, because which will be coming from the solid surface. And if I consider the heat flow over here, I am taking a small region to say that what are the things are happening. Here of course, in this solid surface there will be conduction of the heat, right. This will be the heat. If I consider this, there will be in this region there will be heat which will be coming into here due to the conduction, and there will be also the convection which will be coming over here. Let us say this is your convection, and there will be also the solid phase conduction from this region onwards. This will be solid phase this thing. So, I can say this is Kf dt by dr at this point, and there will be also the, as I told, there will be convection because of the movement of the fluid which will be taking place, and there will be also the heat the convection which is equal to Hg into delta T, and then one can have a heat balance just to find out what it would be, and there is a temperature here, this Tf it will be having, and this is your surface temperature, this is known as surface temperature. And keep in mind that this surface temperature, it moves from Ts, at this point this is your Ts, and it goes on increasing and reach a maximum temperature in the flame surface, and then of course, it decreases, and whereas the velocity will be increasing. Keep in mind that this velocity is being taken as a parabolic in nature, but there will be some increase in velocity due to increase in temperature, which is not being depicted in this figure. There will be boundary layer, this is your hydrodynamic boundary or aerodynamic boundary layer, you can say, and this is your thermal boundary layer. This layer is basically thermal boundary because you can define here. And if you look at the, it's quite complex in nature, and we can say that there will be basically the mass whichever is coming over here, and this there will be melting of these surfaces because the gasification will be going on and also the pyrolysis. So, I can say that whatever heat is coming over here, let us say due to the heat conduction, right, due to conduction of the gas phase, and that is being utilized here for the regression of the solid surface. So, by neglecting the radiation and convective heat transfer, we can have a heat balance at this surface. If you look at this surface, and I can say that this kg dt by dr, and keep in mind this is your r direction, this is your x direction, r is equal to 0, I can have rho f fuel r dot and delta h v, and this r dot is basically regression rate, and rho f is the density of fuel, and delta h v is your heat of vaporization of the solid fuel. And one can also solve this boundary layer equations for energy, and then of course, for your fluid flow, and then one can derive an expression for regression rate, which is quite complex. But what we will be doing, we will be looking at the experimental results, because the processes are quite complex to model, and people have conducted experiment and they have come up with the semi empirical relationship for the regression rate, that is R x is equal to C into G power to the m, whereas G is the total mass flux is equal to rho g V g, and this is, if you look at the gas, this is your density of the gas, and this is V g is the velocity of the gas, and m is the mass flux coefficient, and C is your constant. And this is a very generic relationship for the regression rate, and for polyethylene and hydrogen peroxide, R dot is equal to 8 g power to 0.45 centimeter per second. Keep in mind that this is valid for the characteristics of velocity of 1530 to 1590 meter per second, and the phi is the equivalence ratio is 0.1 to 0.2, and chamber pressure of 3 megapascal, and this will be valid for that this relationship. So, you cannot really use for other cases, and whereas the more elaborate and semi empirical relation for the regression rate is basically rho f into r dot is equal to 0.038 g, g is your total mass flux, and Reynolds number R e x power to minus 0.2, and B is your 0.23, and where the B is basically ratio of delta S T divided by delta H V, and keep in mind that this is your enthalpy differences between the fuel and fuel surface and flame. And delta H B, as I told earlier, it is basically the heat of vaporization, and this is known as the blowing ratio. And because of this heat being coming from the flame to the surface, and there is a heat of vaporization which will be supplied by that, there will be also generation of the gases by the burning of the solid fuel. So, that became rho V power S divided by the rho g V g, and also we put it C f divided by 2, whereas C f is equal to skin friction coefficient. And keep in mind that this is basically being developed by using the Reynolds analogy, therefore, skin friction coefficient comes into picture. And beside this Reynolds number, if you look at the R e is equal to rho g V g x, x will be any distance from wherever you are looking at this velocity, this is your x, and divided by mu g. And if I just expand this one, I will get a very interesting result, that is basically this equal to 0.038 g power 0.8 into in the bracket x divided by mu z power to minus 0.2 and b 0.23. So, this indicates that regression rate will be dependent on the x, that means the distance from the its beginning to the toward the end, and this regression rate will be changing along with the length of the fuel grain, and it will be also depending on the mass flux. If the mass flux increases, then it will be also regression rate will be increasing, and it will be inversely proportional to the density of the fuel. So, it is also dependent weakly on the blowing ratio. So, it is a quite a complex relationship as compared to the solid propellant relationship for the regression rate. So, with this we will stop over here. In the next lecture, we will be discussing about the more aspect of hybrid propellant rocket engine. Thank you very much.